right is what the sun looks like during solar maximum. We call a solar active region, or what you would probably call sunspots. If you looked at the sun properly filtered through a telescope, you'd see dark spots on the surface. Studying the sun, it changes so much. And I have an animation, hopefully, that's gonna play. And, whoop, let's back up one. Let's try to get that animation. While I'm trying to get the animation, note the scale of the Earth. It's tiny compared to the sun itself. Well, come on, sun, rotate. Can I have some help from the booth? No? Well, I guess it's not good. It did when we practiced. Okay, the animation itself shows what the sun looks like as it goes through a rotation, and it shows the loops, and those are the loops that you can see. Well, the bright areas that you see on the edge of the sun, those loops are magnetic loops, and they contain gases, and those loops are constantly changing. And the ones that you see on the face of the sun are also constantly changing, and sometimes they erupt. So let's, whoop, okay. So what is the sun? What are its parts? Quickly, the sun has a core where the energy that comes out, that we get here on Earth, is created. It's created from thermonuclear explosions, where hydrogen combines with hydrogen and makes helium. And the temperatures to do this are very, very high. Has to be about 15 million degrees Kelvin. And don't worry about if you don't know what the Kelvin scale is all about. 15 million of anything is hot. So that energy comes out. It is the energy moves. The energy is produced and moves through by conduction. So one bumps into another or bumps into another. And then it gets to an area where density is not high enough to support energy transport through conduction. That's fancy words. And then you start carrying energy through photons. So photons of light, high energy light, travel through this inner part. And then they get to a region that we call the convection zone, and then convection takes over. And then you get to the surface called the photosphere, and that's the surface that we see every day in visible light, and that's where you see sunspots. Then above that is the chromosphere, and above that is the corona. And the corona is named after the Latin word which means crown, and it is kind of the crown of the sun. And in solar physics, one of the biggest questions is, why is the corona so hot? It's not as hot as the core, but it's still millions of degrees. And this is interesting because the photosphere, where we see the sunspots, is much, much cooler. It's around 6,000 degrees. The sunspots themselves are around 4,000 degrees, and they are dark because they are cooler than the surrounding area. But think about it. If you stand in front of a fire and you move away from the fire, the farther away you go, the cooler. But that's not the way it works on the sun. You get to the photosphere and the temperature is cool, relatively speaking. And then you get into the chromosphere and it is slightly cooler, and then you get to an area in the chromosphere that we call the temperature minimum, and then the temperature starts to rise again, so that it's millions of degrees in the corona, and we don't understand why that is. So we also have things called prominences. Those are the loops that you see on the edge or limb of the sun. And we have filaments. And a filament is it looks dark because you see it against the bright background of the sun, but it's actually a prominence. If you saw it edge on, as you do on the left side of that image, it would be called a prominence. And why are they called two different things? Because when they were first discovered, nobody knew that they were the same thing. So they have different names, but they are the same thing. And so you can have filament eruptions, which would be an eruption from the face of the disk, or you could have a prominence eruption, which would be an eruption from the edge or limb of the sun. And let's see if this animation will work. There we go. So down on the bottom, there's a filament labeled, and it is erupting right now. That's what it would look like. And sometimes those things fall back to the sun because of the sun's gravity, and other times they go on out into interplanetary space where they can interact with Earth's magnetic field. And that's important for things like coronal mass ejections. We have flares, which are actually brightenings on the surface of the sun, or actually, we typically see the flares in the chromosphere and in the corona, and they are just photons. They're just light. It might be high energy light, like X-rays, but it's just light. A coronal mass ejection, on the other hand, produces mass. They're tiny particles, they're protons and electrons, but a coronal mass ejection pushes mass out into interplanetary space, and that mass can interact with Earth's magnetic field. So why would NASA care about studying the sun? Well, because of this, because of space weather. And space weather can affect all the systems that you see on this slide. It can affect ground communications. It can create something called a ground-induced current, so that those charged particles that I mentioned, the electrons and the protons, interact with Earth's magnetic field. They can make it all the way to the ground. They cause currents to flow in the ground, depending on the geology of the area. And those currents can then flow in the ground to large transformers. This happened in 1989, when there was a power outage in Quebec and the northeastern part of the United States that lasted for several hours. And people were stuck in elevators for several hours because they had no power. And it was caused by ground-induced currents from a coronal mass ejection that interacted with Earth's magnetic field. So NASA wants to understand more about these events, what causes them, how can we predict them, and we actually have a space weather program that's going on right now, and NASA's looking at establishing a space weather program office, and where that office will be, that is at what center it will be located, is still to be determined. Another effect of space weather is that airline flights can change their direction, their altitude, and where they fly. So normally, if you're flying, say, from Canada to Europe somewhere, you're going to want to fly north and fly over the poles because it's a shorter distance. And you want to fly high because the air is not as dense there, and so you're not using as much fuel. If there is predicted a space weather event, those airlines lower their altitude and they fly farther south away from the poles, because this is where those particles can enter into Earth's magnetic field. So you want to be away from that area as far as possible. So that's why we have aurora in the northern part of the country, or if you're in the southern hemisphere, in the southern part of, say, South America, and not as much in the northern part of each hemisphere, or southern, northern, depending on where you are. So if you're in the United States, it is very unlikely for space weather events to occur even this far south. Sometimes there are aurora here, but not that often. Sometimes there are aurora as far south as Puerto Rico. But those are large events, and I guarantee you'll know about it if it's about to happen. So, we're going to talk about eclipses too, not just the sun. But the sun is involved in eclipses, and the moon is involved in eclipses, the types we're talking about, and Earth is involved in eclipses. You have to have all three of those things. So if you have a total solar eclipse, take a look at the sequence that's on the top of this slide. You first have partial phases where the moon is just beginning to cover the sun, and you get those little crescents. And then the moon completely covers the face of the sun, or the photosphere, and you get totality, and you get the corona around the edge of the moon. And sometimes you can see those prominences around the edge of the moon as well. So remember that when you're looking at the sun with your eclipse glasses on during totality, look for those prominences. You might not be, unless they're very large, you might not be able to see them unless you have a telescope, but it is something to look for. So what happens when we have a total eclipse is that the moon is moving in between sun and Earth. And it just so happens that the moon is, on average, just the right distance and just the right size to completely cover the face of the sun. In time, the moon's orbit will move farther and farther and farther away from Earth, so eventually we will not have total solar eclipses anymore. And that kind of brings up this question: what's the difference between an annular eclipse and a total eclipse? In this case, the moon is not at its average distance, it's a little bit farther away or at its farthest point, so it looks smaller, and it doesn't completely cover the face of the sun. So you get a ring of light around the edge of the moon. And the ring is actually called an annulus from the Latin word, which means ring. And so people have coined the term ring of fire eclipse to refer to this type of eclipse. And this will happen on October 14th. Every person in the United States will have the opportunity to see a partial eclipse on that date. And if you happen to be in special places in the United States or in Brazil even, you could see the ring of fire. Well, so NASA wants you to get involved. How can you be involved? Well, one thing you can do is talk about what you've learned here today, and with the handout that you have, along with your solar viewing glasses, we're trying to avoid using the word eclipse glasses, because you can use those to look at the sun at any time. Just remember to put them on before you look at the sun, look down, away from the sun, and then take them off. Don't look at the sun without those eclipse solar viewing glasses on. And I say look at the sun at any time because sometimes sunspots are so large you can see them without using a telescope. And because of that solar cycle I mentioned, the number of sunspots is going to continue to increase with time for quite a while. We expect the maximum of that cycle to occur anytime after January 2024, but probably in 2025. So because the activity of the sun is increasing, it's possible you might have a sunspot large enough to see without using a telescope, just using your solar viewing glasses. And also, it's also possible for more coronal mass ejections to occur. And wouldn't it be neat if one of those happened during the total eclipse next April? So there are some citizen science projects for you to become involved. And I've listed a few here that require just a little bit of technology and then a lot more technology. And if you're not satisfied with those projects, I got a whole list here. Now, this alphabet soup is something I would not normally do on a slide. There are way too many words on that slide. But I wanted you to get a feel for how many activities are possible. These are things for you to investigate for the annular eclipse and for the total eclipse. One of the things that I'm most interested in is, let's see if I can find it. Where did I put it? Well, there's Sun Sketcher 2024, which will use a cell phone. And the app to do that is under, it's under development, and it's not quite ready yet. They're probably gonna have some beta versions ready maybe next week, but I don't believe anyone here, including me, can get hold of one. But they expect them to be quite ready by 2024 April eclipse. And somewhere in there is, well, there's study the Earth's atmosphere and study radio waves up there close to the top. Those are two that I find really interesting as well. So take a look at that list. If you're interested in getting this full list, you can contact me. My email address is on that handout that you got, and I can send you this slide. This one will email very easily. Eclipse safety is really important. I mentioned how to use your solar viewing glasses. Each time you use those, take them outside, hold them up so that the sun is shining on the mylar eye area. Hold your hand underneath. If you see any light coming through that mylar, don't use them. So you gotta look for just pinholes in the mylar. And if you see that, don't use them. If the mylar starts to separate from the cardboard, don't use them. But you can do other things. You can use indirect methods. For the partial phases of either eclipse, the annular, and this will be neat for this area around here on October 14th, stand under a tree and you will see little crescent suns projected onto the ground. That's essentially a pinhole projector. And you can make those too. You can use a colander. Go into your kitchen, pull out a colander, hold it to the light, and you'll see little crescents shining through those holes in the colander. The other thing you can do, you don't need any equipment, interlace your fingers. and the light will shine through the interlaced fingers that are acting like pinholes, and you'll get projected on the ground little crescents. We do have some accessible STEM resources that are available. Eclipse Soundscapes is really a good thing to try to get involved in. And also, we have the Braille book on eclipses. So if you are interested in Braille books, there's sservi.nasa.gov, and they'll put you in touch with the folks to get those books. These two maps, well, it's one map of the United States with two paths on it, show you where the eclipses are going to be maximum. So the one on the left is the path of annularity. If you are anywhere inside that region, you will see an annulus of light around the edge of the moon. If you're outside that path, you will not see the annulus of light. You'll see the partial. Now, even if you are inside the path of annularity, you still have to wear those solar viewing glasses in order to look at the sun, because even that thin ring that is around the edge of the moon is too bright, and you'll damage your eyes if you're not using the proper protection. The path on the right side, the one that comes up through Mexico and exits through New England, that is the path of totality. And so you folks are going to be involved in a total eclipse of the sun, which will be a really, really inspiring thing for you to experience. And I will say, I've observed 5 total solar eclipses. My first one was March 1970 from close to Savannah, Georgia, Fort Jackson, as a matter of fact. And it was totally cloudy. I was fortunate, lucky, I don't know what. There were a couple of folks there, from around New York City, who had, and this was 1970, so this was not common. They had a small TV that they could plug into their car. And so there were, I believe they were NBC reporters in Mexico, and the path went through Mexico and into Florida and through Georgia. And I got to see the total eclipse on TV. But I experienced it in person, and that was very, very special. It was totally cloudy, but it got dark in the middle of the day, and so crickets started chirping. They weren't chirping before totality, even though it was cloudy. But crickets started chirping. I could see birds going into the trees to roost. Those were really the only animals that I could observe during that short part of totality. But it was an awe-inspiring experience nonetheless. And the other 4 that I've experienced, I got to see totality. And the last one, of course, was 2017. I was in Clarksville, Tennessee, at Austin-Peay State University, and we had groups of students from the DC area, from the Space and Rocket Center, and then locally from Huntsville, and also from Austin-Peay. And we observed cows, and we observed birds, and we observed bees and crickets. And some of the cricketeers, as they were called, the students who were observing the crickets, they happened to notice during totality, or actually leading up to totality, as the light got dimmer and dimmer, and it got a little bit cooler, there was a pond that they could see. And they noticed that turtles were coming out of the pond and resting on the bank. And as soon as totality ended, those turtles went back into the pond. Interesting effects, things to look for. If you're interested in staying up to date on what NASA's doing, you can subscribe to the NASA Eclipse newsletter, and feel free to grab that QR code. And I thank you for your attention. I will take some questions, but before we start that, I just want you to know that NASA will have, for both the total eclipse and the annular eclipse, annular is in October, we'll have streaming sites. For the annular, they'll be in Kerrville, Texas, and Albuquerque, New Mexico. For the total eclipse, they'll be in Kerrville, Texas. So with that, let's see if anybody has any questions.
If you have one, raise your hand, I'll bring the microphone.
I'll try to answer anything.
Tell us more.
So like at what time will like total eclipses not be possible?
Thousands of years in the future, and I forget the exact date. Sorry about that. I can tell you that the sun will only last for another 5 billion years or so.
Oh, I won't be around for that.
Neither will I. I saw a hand over here. Oh, sorry.
There's a small hand over here.
Okay. Yeah, I see.
Is there going to be science there?
Is there going to be science there?
Yes.
At the eclipses? Yes. Lots of science.
Over here somewhere.
No, not me, the one next to me.
Is there going to be a way to predict or prevent the aurora?
The aurora, we don't really care about preventing aurora. They are just the effects of charged particles interacting with Earth's atmosphere at fairly high altitudes, and they produce colorful, shimmering light. But there's no detrimental effect. The problem comes when we have coronal mass ejections, and when these events happen from the sun, there's mass, although it's charged particles like protons and electrons, it's small mass, but it's still mass, traveling at near relativistic speeds. So when you got mass plus high velocity, you got high momentum, and then they slam into Earth's magnetic field, and because Earth has a magnetic field, and these are charged particles, they spiral down lower and lower, and the depth that they can penetrate depends on the speed of the coronal mass ejection and how much mass is in it. And we have a satellite that can give us about an hour's notice of whether or not that CME, as we call it, coronal mass ejection, is going to interact with our magnetic field. And power stations do know that they have to take action at that time.
What made you want to go into this field of work?
Interesting question. I always wanted to be, always wanted to work for NASA. From the time I could, like third grade or something. And I was always fascinated with the night sky and the stars. And sometime in high school, I did a term paper on sunspots. And that was interesting. And then I went on to college, and I was considering graduate school, trying to figure out what I was going to do with my life once I got a bachelor's degree. And an opportunity came up for me to do an internship in Huntsville with a solar astronomer. And I worked there for a summer, and they offered me a graduate co-op position, which meant I had to leave Atlanta and go to Huntsville to graduate school. And I found the work interesting, so that's what I did.
Hi, I'm Owen.
So am I.
I've been around since before the space race and all of that, but I'm trying to see if NASA has made a correlation between the rockets launching from Earth through our protected layers
The
of
ozone.
atmosphere and our extreme weather conditions that follow post-launch.
The short answer to that is no, there's no correlation. The longer answer is yes, launching rockets does have an effect on the ozone layer. It punches a hole through it, but it quickly recovers. And the effect of not having an ozone layer is that you have more ultraviolet light getting to the surface. And the ultraviolet light can damage skin. Of course, we know about skin cancer. It can also damage plants. But this ozone hole that the rockets create is very small, and it does close up really fast. So the damage is very minimal, if any. And they also occur over the ocean because they launch in that direction.
So you mentioned that there are times where we can see those sunspots outside of the eclipse. Does anything ever go out, like an alert or social media or anything like that, to let us know those things?
Yes. Short answer. Longer answer is you won't see sunspots during the solar eclipse because the moon is going to be covering the face of the sun where the sunspots exist. What you will see during a total eclipse is the corona outside the edge of the moon. And that is actually something that you don't easily see from Earth except during a solar eclipse. We do have satellites that will create an artificial eclipse. They have something called an occulting disk that fits over the face of the sun and blocks the bright light, and so then you can see the corona. And we study coronal mass ejections from those satellites using that technique all the time. The problem is the coronal disk, that occulting disk, does not get down to the photospheric layer. So you miss a section of the atmosphere. And what we're trying to do right now is connect everything from the photosphere through the chromosphere into the corona and to Earth or other planets, because eventually, if we have people on Mars, they're going to want to know about coronal mass ejections too. So we want to be able to predict what's going to happen at many places during at least the inner solar system out to Mars. Great question.
I don't need the mic. So whenever, sorry, my brain just stopped working. If you were to make your own glasses to observe the sun at home, would using welding shield, like a welding or shield work just as well as, say, these?
I would not recommend making your own eclipse glasses, solar viewing glasses at home. However, there is another way that you can view the sun safely directly using number 14 welder's glass, which you can buy from a local or online welding store. I'm not sure of the rating of the welder's goggles. If it's number 14, that would work. But the number 14 welder's glass I've seen looks like a slide, a microscope slide, but you hold it up to the sun and you don't want to walk around with it over your eyes because you'll fall, because you can't see anything except the sun through it. And that's the same way it is with the solar viewing glasses.
Thank you.
And also on that note, on the American Astronomical Society's website. So you can go there and find other tips on eclipse safety. You can go to the NASA websites and find other tips on safety during eclipses.
Why are some eclipses longer than others?
That is an excellent question. And it depends on the geometry of the eclipse. It depends on the moon's distance from Earth, mostly, and the orbit of Earth around the sun. So when all of these combine, you might be able to get a 7-minute eclipse, which is the longest possible. And then it goes down from there. And by the way, if you're not doing anything in 2027, there is a total solar eclipse that is viewable from Luxor, Egypt, that will be 6 minutes and some odd seconds long. I'm hoping I can go.
I can talk about that. Not here on video. Sorry.
Can the sun cause an EMP?
Can the sun cause an EMP? Not really. It's an electromagnetic pulse. And the electromagnetic pulses are caused by nuclear weaponry. But the sun is so far away that it doesn't really do that. It can cause a lot of changes in our radio communication. It can cause changes in GPS, but that's not really an EMP.
Mr. Tucker, the Dean of Students at ASU-Beebe, would like to interject that there will be certified glasses available for students. Is that what you'd like me to say? Sure, okay. So students be looking for that. Thank you so much for being here with us today. Students, thanks so many of you for coming. Ms. Adams, have a great day. We really appreciate it. Thank you all.
Thanks, everyone.